All right, 2.3 applies slope, midpoint, and length formulas. So we're going to look at ways to apply these formulas in situations. All right, now we can use analytic geometry to determine properties of geometric shapes in the sense that a graph can often be helpful for understanding a problem. So we can use the analytic geometry. So let's say we're looking at a geometric shape. We can use things like slope, midpoint, and length to be able to answer questions about geometric shapes. Now, obviously, in order to see a geometric shape, we should have some sort of graph, and this graph is usually very helpful for us to understand the problem. So a graph is a good idea to always have. Now, some things that are important that we use analytic geometry to solve is lines such as altitude. An altitude is the height of a triangle. It represents the height of a shape, and it doesn't necessarily have to be a triangle, but we usually associate this with particularly triangles. Now, it must be drawn perpendicularly from the vertex to the opposite side. Now, very important to note is that if you look at the example below over here, there are 3 altitudes for any given triangle. It always extends from a vertex to the opposite side. Now, some of you may be thinking, well, that's an equilateral triangle. No, folks, it doesn't matter what kind of triangle you draw. The altitude always goes from a side to the opposite side. Not at a midpoint. That is not necessarily true. The altitude is just drawn perpendicularly from the opposite side going through the midpoint. Note that whichever altitude you choose, all 3 altitudes always meet at a specific point. And that's true if it was medians that I drew or even right bisectors. It is always true that they will meet at one single certain point. Now, how come I drew the medians in different places like this? I want you to understand how that was drawn. So I'm going to grab this upper triangle right there. We're going to grab them, and I'm going to turn them around so that you can physically see how you would draw an altitude. I could take this triangle and turn it any which way I want. The thing is that in order to draw the altitude, let's say I wanted to draw the altitude from the side here, this side. Do you see it? I turned the triangle, so you would turn your page in order to have the bottom of the side that you're looking at to draw your altitude at horizontal to you. So you would turn your page or turn your computer screen so that you could have this as your bottom side, and it's always on a piece of paper. Now I want to draw the altitude from this side to this given point. You're thinking, how's that possible? I can't draw a right angle to this side. Well, folks, you can. What you need to do is extend the side of that triangle. So how I'm going to do that, whoops, I don't know what happened there. Let's go back and see what happened here. I think we jumped a couple of screens there. There we go. So we're going to make this particular triangle and find the altitude. How we're going to do that is extend the side just like this. So extending that bottom so that from the vertex, that would be this point, we're going to go straight down to make a horizontal line. Sorry, a vertical line that is perpendicular to the horizontal base. So again, a perpendicular line that is perpendicular to the base of the triangle we're looking at. So that's the altitude we're looking at here, folks. Okay, so I'm just going to quickly draw that again. Sorry, just connect that. There we go. All right. So that is the altitude from this vertex. From this vertex here, this would be the altitude or height of the triangle. Now, let's say I wanted now to find the height from the third vertex. How would we do that? So what I'm going to do is snatch it again, and we're going to turn it one more time. So again, we take the triangle that we have, we're going to snatch it, and I am going to turn it. So now the last base is at the bottom. So that's exactly what you would do with your piece of paper. Extend it so that last base is on the bottom. Exactly what I did, just a second. He just got larger. We want to make him on the base so it's a right angle. And again, we want to draw that altitude. We draw that altitude by extending our base. Here we go. I'm going to extend it in blue. And I want to draw my altitude line coming from this vertex. Funny enough, there's an A there. But the idea is we want to make our altitude here. And that's what I'm going to do, is draw the altitude. Let's use green to draw our altitude. Draw our altitude that is directly vertical to the horizontal base. There we go. And this is vertical to the base. And the base is on our horizontal level, so we made a perpendicular altitude. And if we extended every one of these lines, so this red line, I extend this way, okay? And then I extend this red line over here, and I extend that red line across. Oops, just a second. I think it got attached somehow. What would happen is that all my altitudes will actually intersect at the same point. That is true all the time. So interesting. I think this is quite interesting for us to see and draw. So I just wanted to show you guys how we would draw them. And so I erased it all, folks, so we can go back to what we had originally. All right, on to the next problem, to the real question. Here we go. Example 1. Find the area of a triangle with vertices X, Y, and Z. What do we do here? Well, this would be considered an inquiry level question because I give you nothing. I give you coordinates, and that's it. I want you to find the area. How are we going to solve this? Well, first off, we need to graph it. There's X, Y, and Z. We connect them, and that creates our triangle. We also know that the area of a triangle is, that's right folks, area is equal to base times height divided by 2. Now, base times height divided by 2, we're forced to draw an altitude. Oh, I just drew one here. Is that the altitude we want? Is that a good representation of our altitude? Do we know the length of this altitude? Because if we knew the length of this altitude, find the length of this base, and we can use that to find the area of the triangle. Well, how do we find the length of that altitude, you may ask? Maybe we need to find this point. What is this point? Some of you might be thinking, oh, it must be a midpoint. Wrong. Not necessarily. We actually have a problem here. We don't know what this point is. Now, we could use elimination and solve for the point and then find the length and find the length. Probably not a good idea. I wouldn't recommend it. Is this some sort of triangle? Some special triangle that might help us get the right answer? That's what we need to find. So, if we have an isosceles triangle, then I know I can build my altitude, and that altitude would actually be equal to the median. That's a property that's very interesting. So the altitude and the median would be the same if we use the vertex of the two sides that are equal in an isosceles triangle. That would help us because we could find this length no problem because at this point would end up being a midpoint. Or we could have a situation where we have a right angle triangle. And if we had a right angle triangle, guys, we have our base. we have our height, and we can use this as our base and height to find the area of the triangle. So we have to investigate this particular problem further. And how are we going to do that? Well, this is what we're trying to avoid. We're trying to avoid a situation where the altitude is a point where we have to use elimination or substitution. That would be the worst case scenario. So let's check the lengths of each of the sides. All right, folks, the lengths of each of the sides. So distance of xy, plug it in. You get the value of root 20. The distance of yz, plug it in using the coordinates, and you find root 45. So again, look, we have root 20, root 45. So that's xy right here, and yz, that's right here. So it's root 20 and root 45. And the last one turns out to be root 65. What does that mean for us? Let's go back. We have root 20. Oops, how did that happen? We don't know. All right. Root 20, we have root 45, and we have root 65. Those are the three pieces we do have. What can we do with this? Well, we know it's a scalene, so we don't have an isosceles situation where we could find the median would be the same as the altitude. So we need to look at another way. What else could we check for? Do you remember what I was telling you? That's right. We could check and see if this is a right angle triangle. We're checking for perpendicular. And root 20 squared, that's this first one, plus root 45 squared is checking it to see if it's equal to root 65 squared. And lo and behold, folks, left side equals right side. So we have found out that the angle is a right angle triangle between xy and yz. There's a right angle inside there because the two small sides will make up a combination for the third side. And guess what? We can solve for the area of the triangle. But I'm running out of time surely on this video, so we've proven that it's a right angle triangle. We're now going to find the area of it. So let's go to the next video to show this. See you on the other side, folks.